Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. This is the first module. Title of the module is Introduction of Non-Newtonian Fluids, in which we will be discussing so many variety of details of non-Newtonian fluids, their classification, models, some problems, etc. Those things we are going to see. However, in the first lecture of this module, we are going to discuss only introduction and then basic concepts of this course, which may be related, which may be important in further part of this course. So, why should we need to study these transport phenomena courses in general? There are several types of transport phenomena courses: the analysis of transport phenomena, computational transport phenomena of specific type of fluids like non-Newtonian fluids, etc. Because knowledge of transport phenomena is very much essential in design and controlling of operating conditions of many unit processes or unit operations of a chemical and an associated engineering branches. What happens, let us say we take a few unit operations and a unit process to see how this information whatever we are going to get from the transport phenomena is going to be useful in general in the design. What we have, let us assume we have a pre-treatment unit, right, where let us say some component is being treated for temperature or for purification, something like this, and there is a kind of unit process where some catalysts are there, let us say packed bed or some kind of fluidized bed reactors, something like this, right. So, here the energy is also involved, okay. So, some reaction is taking place, and then after the reaction there is another kind of unit operations, let us say some separation is taking place. So, first one is pre-treatment, then unit process. So, let us say after the purification whatever this material is there coming from this first unit operation, and then going to the unit process where some kind of reaction is taking place. Let us say some gas, some other element B is also being introduced here into the reactions, and there is some kind of energy is also associated with this one. So, whatever the products that you have, let us say you bring it to the separation unit, which is also a unit operation, and then where whatever the products are there, product, byproduct, let us say C and D are the things that you are getting out of it, and then let us say D is a kind of final product, C is a kind of byproduct you are separating. This is how in general we have a kind of flow sheet of any simple process, but there may be many complications and then settings, connections, etc., fittings, etc. More than one unit operations, more than one unit processes are also be there, and then in general they are connected by pipelines, either horizontal or vertical, sometimes inclined also. What happens overall performance here, it depends on the performance of individual units, right. So, how good is the pre-treatment process unit operation is performing, how good is the reaction and the conversion, yield, etc., and then how good is the separation. Everything is going to play a very important vital role in getting the product D, better product D, right. So, we understand that individually whatever the performance is there, that is going to affect the overall performance also, individual performance of pre-treatment. Let us say if you could not able to do the required pre-treatment of purification of ALA. So, let us say impurities that you want to separate. If you could not able to do this pre-treatment properly, so then that reaction is going to be affected, and then so whatever the C and D products are coming, they may also be affected, and then along with this C and D there may also be some kind of impurities, right. So, even if you could do the impurities separation properly in the pre-treatment, then if the reactions this unit process is not performing properly, then whatever the product is there, that is going to be affected. So, it is required in general to make sure that at each and every individual level required change process, right, change process in general, like the flow properties or temperature distribution or pressure distribution or concentration variations, all these things are need to be carefully monitored at each level, right, so that you can have a kind of proper properly performing design. Okay. So we know that these can perform better if we can control their performance properly if we know their velocity distribution, if we know the temperature distribution, if we also know the pressure distribution, if we know the species concentration distribution, etc. If these details we know, if we know at every level, let us say at every level in the sense in the individual unit operations and unit processes, and in addition to that the connecting pipes, in general they are connected by the pipes. These pipe connections may be horizontal, vertical or inclined in general. So in these cases, if you know these distributions of the fluids which are going to be treated in this process, in this entire process, if you know these details, you can control the process properly. You can control the process very properly. So or in general, in these kind of cases, you also need to have some kind of information like friction factor, drag coefficient, Nusselt number, Sherwood number, etc. These things are also important, which are in general again related to the velocity distributions or temperature distributions or species concentration distributions. They may also depend on the properties of the material, they may also depend on the geometry of these things, all these things. So all these things information, the entire accurate information in general, it is very difficult to get from a kind of coursework, because these things are very much complex phenomena may occur. So what we do in general, engineering point of view, we simplify the problem as much as possible and then get the information. So what kind of simplification we do in general in transport phenomena courses, we get a kind of restricted solutions. Numerical solutions you can get for the entire process, and you can get the very much accurate and reliable solution for the entire plant or individual set, unit operations or unit process or individual connecting pipe. So that can be done, but that cannot be done on field very immediately. So sometimes the restricted solutions will give us a kind of control over the process, right, both design as well as the control. So that restricted solutions in the sense, let us say laminar one dimensional flow, that kind of restrictions, the flow is varying in only particular one direction, it is not varying in the other direction, those kind of restrictions. Temperature variations may be there in multiple direction, but you take in such a way that whichever direction more temperature variations are there, those kind of things you take into the consideration and do the analysis to get a solution that we can say restricted solution, right. Even not necessarily for this laminar flows, even in the turbulent flow also we can have some kind of restrictions, and then we get the analytical solutions, right, analytical solutions that we can quickly do on a pen, on a paper, wherever we have any issues, and then we can have a kind of qualitative information, if not exact information, qualitative information mentioning which is going to be affecting more in the process, which particular parameter or which particular mechanism, transport mechanism or which type of transport is going to have a leading role. Those kind of things we can draw out. Those kind of information in general we can get from this transport phenomena course. So let us say in general we get velocity distributions, volumetric flow rate information, then temperature distribution, then also species concentration distribution, etc. In general, they again in turn they can also be represented in terms of the friction factor, drag coefficients or Nusselt number or Sherwood numbers, right. So once we have this information, a priori information, we can control very much the process as per our requirement. A few examples, if you see knowledge of transport phenomena in general, flow through pipes. The flow through pipes is in general very first problem that we take in transport phenomena, because we know, as we have seen here, from one unit operations to the other unit operation or unit process or vice versa, they are connected by pipes. So, in the pipes also some kind of momentum transfer, some amount of heat transfer, some amount of mass transfer may be taking place individually or combined, or more than one transport process may be occurring. That is the reason in general we take flow through pipes as a kind of standard problem in general to start with this in these transport phenomena courses. Then also we have flow and heat transfer from cylindrical particles and spherical particles to surrounding fluids, diffusion of spacing from falling film, etc., like in paper industries or some polymer industries, evaporation of column of liquid, sometimes boundary layer flows past flat plates, associated heat and mass transfer to the surrounding fluids, and so on. So, like in a chemical industries, any part you take, starting from the pre-treatment to the separation of the product to get the final desirable product, at each and every level there is some amount of momentum transfer, heat transfer, mass transfer may be existing either individually or combined, two processes together, or all three processes together, or not only these three processes, sometimes reaction is also included. So that is the reason this transport phenomena is going to be very much essential for chemical and related engineering branches. So then why non-Newtonian fluids? We understand the importance of the transport phenomena course, then it is also needed to know why non-Newtonian fluids, because this course is specifically transport phenomena of non-Newtonian fluids. So because these non-Newtonian fluids are almost ubiquitous in many industries of chemical and related engineering disciplines, like for example, we take the polymer industries. Polymer industries, it has been found that many of the polymer solutions in general, or the polymers that are when they are dissolved in some kind of solvents, those polymer solutions in general, they show some kind of shear thinning behavior. Many of them show shear thinning kind of behavior. Of course, they also show other kind of behavior, like viscoplastic, time dependent, and some polymers also show the viscoelastic behavior also. So that is the reason the non-Newtonian fluids are expected to having a vital role in polymer industries. In petroleum industries, tertiary oil recovery, that is being done in general by using polymer solution, where what is being done in general after taking the sufficient oil. So most of the oil, when it has been drilled out, there may be some oil trapped in the porous structure of the rock. So usually some polymer solution is sent into this porous structure, so that the oil is replaced by this polymer solution, and then that oil can also be recovered, right. So for this purpose, several types of non-Newtonian polymer solutions are used. Also drilling is also one of the very much important factor in petroleum industry. So many drilling muds in general, they show viscoplastic behavior. Some drilling muds also show a kind of shear thinning behavior, right. Similarly, like food industries, like if you take chocolates, etc. Chocolates are in general solid or semi-solid form initially. That viscosity is decreasing by applying the shear rate. You take some kind of proprietary soups, right, and then what you do, you taking a spoon, you rotate the soup in a particular direction, in one particular direction for some time, right, and then you can see when you are rotating some kind of circles you can see on the surface of the soup in the direction of the rotation. But when you stop rotating, these rotations will still move in the direction of the rotation, even though it stopped rotating, and then they stop for a while, and then they try to come back come back one or two circles back. So that what does it mean? These proprietary soup constituents, whatever they know their background, and then they try to go back to their initial position. They may not able to go completely to their initial position, but partially they may go back to their towards their initial position. So that indicating these soups are also having a kind of elastic behavior. So viscoelasticity is also one of the important type of non-Newtonian behavior. Similarly, cosmetic industries, let us say lotions, if you take body lotions, you take and then rub between your arms, what happens initially, body lotion is a kind of viscous material kind of thing. When you are rubbing, it becomes thinner and thinner. The viscosity is decreasing by rubbing. Rubbing is a kind of act that initiate that shearing causes the shearing. So, with the shearing the viscosity is decreasing. So, the shear dependent viscosity you can see there, right. So, you do not want it to be coming to its initial position after rubbing again. So, those kind of things that you can see in cosmetic industries also, these non-Newtonian fluids are very much essential. Similarly, biological fluids, sometimes saliva, blood, synovial fluids, they also show some amount of non-Newtonian characteristics depending on the range of shear rate being applied. Likewise, if we keep on listing, we can see applications in mining industry, paints industries, beverages industry, cement industries, pharmaceuticals, where many syrups they display different types of non-Newtonian characteristics. Even the tablets, before making the pelletizing or making tablets, the whatever the suspensions are there, they also show a variety of non-Newtonian behavior, where the viscosity of the suspension changes either by the shearing or by the time, right. So, like this, if we keep on listing the industries related to the chemical engineering discipline, we can see these non-Newtonian fluids may be existing in almost every industry. So, that is the reason transport phenomena of non-Newtonian fluids is going to be very much important. Why very much important? One simple example we take, let us say we are going to study in the due course anyway. In general, let us say flow through pipe, if a fluid is flowing through a pipe, let us say Newtonian fluid. So, in the fully developed region, what is the velocity profile, the distribution of the velocity profile, which shape of curve it gives? We know that for a Newtonian fluid, it has a kind of parabolic structure like this, right. But if you have a kind of shear thinning fluid, that what happens, you can have a kind of flatter distribution like this. If you have a shear thickening fluids, you can have a kind of sharper distribution like this. So, let us say power law model, n is a kind of behavior index. If n is equals to 1, that power law behavior is same as a kind of whatever the Newtonian behavior. N less than 1 in the sense shear thinning behavior, n greater than 1 in the sense that shear thickening behavior. That is, with the shearing, the thickness the fluid, that viscosity increases. For shear thinning fluid, with the shearing the viscosity decreases. So, for different types of fluids, for the same pipe dimensions, but the only type of fluid has been changed. So, then we can see that this fully developed flow within the fully developed flow region, the velocity distributions are changing very much drastically, right. So, definitely, let us say if you start designing your process assuming the fluid is going to be Newtonian fluid, then friction factor in this case, as in general we have 16 by Re. So, but when you start designing with these things, but when you use this design for a kind of power law fluids, non-Newtonian shear dependent viscosity fluids, then you are not going to get the same performance as you expected for a Newtonian fluid, because here this F is going to be not only going to be function of Re, it is also going to be function of rheological parameters that we are going to derive these relations anyway in subsequent modules. So, if you are intended to use the non-Newtonian fluids, or if you are intended to have a kind of non-Newtonian behavior in your process systems, then it is always better to apply the principles of non-Newtonian fluids in the designing, right. If the design is already there, so then using this non-Newtonian behavior, because of this non-Newtonian behavior, whatever the modified relations are there, those relations should be used, and then accordingly operating conditions should be changed, or the expression, the equations corresponding friction factor or the Nusselt number or Sherwood number correlations that you are going to use, they should be based on the non-Newtonian fluids. Momentum, heat and mass transfer of non-Newtonian fluids with or without reaction, that is what we are going to consider in this lecture, in this particular course, because we understand these momentum, heat or mass transfer phenomena of non-Newtonian fluids, they are going to play vital role in design and are controlling operating conditions of these industrial settings. That is what we are going to see. So, a priori information about the performance of these fluids, especially different types of non-Newtonian fluids in variety of industrial settings, can be achieved right. If not that we are going to consider all the industrial applications in this course, at least from the fundamental whatever that we are going to do in this course, using those principles we can get this kind of a priori information for any given applications where non-Newtonian fluids are playing vital role. So then let us start with the transport phenomena. So transport phenomena is in general include three closely related topics like transport of momentum, transport of energy, transport of various chemical species. Transport of momentum may be related to the fluid mechanics, transport of energy may be related to the heat transfer, and then transport of chemical species may be related to the mass transfer. So when we have individually studied in general in your UG courses fluid mechanics, heat transfer and mass transfer, then why should we study a transport phenomena course separately? The very first reason is that in general they occur simultaneously, but not kind of individually. So happening either individual momentum transfer or individual heat transfer or individual mass transfer is a kind of exception rather than a rule. Okay. And then in general this fluid mechanics, heat transfer and then mass transfer courses, what we do, we take macroscopic balances considering only input and output in general without worrying the what is happening inside the system for a given change, whether it is momentum transfer or heat transfer or mass transfer. So those additional details can also be obtained from this transport phenomena course. Why those additional informations are in general important? Let us say we have a kind of mixing. We know that when these things are added A and B and then have done the mixing kind of thing, so then we have a kind of uniform solution coming out, let us say. But what happens in these things in general, let us say in these corners, in this corner whatever those constituents are not being mixed properly in general, that has been found, right. So how much it is not mixed, how much it is important to be considered, those things depends on the applications. But if you know the what is the velocity distribution at each and every location within the system, then you can find out what is the reason that these things are not being mixed properly mixed at the corners, or the transport is not occurring at these corners, that you can draw, and you can know those things, and then accordingly you can do those corrections, right. So in general these things are very much essential in kind of if you are dealing with a kind of expensive materials. Okay. Then governing equations describing these transport phenomena are also closely related, right. What are the governing equations that are describing these transport processes? Momentum transport is in general defined by the continuity equation and then momentum equation, or conservation of mass and then momentum. And then heat transfer is in general related to the temperature distribution equation or energy equation. Similarly, species concentration equations. Let us say if I write momentum equation, what I can write, dou v by dou t, let us say Vx plus Vx dou Vx by dou x plus Vy dou Vx by dou y plus Vz dou Vx by dou z is equals to minus 1 by rho dou p by dou x plus mu by rho dou square Vx by dou x square plus dou square Vx by dou y square plus dou square Vx by dou z square plus let us say some kind of gravity terms if you have something like that. I am not writing y component and z component of momentum equation. So dou by dou t of t plus Vx dou by dou x of t plus Vy dou by dou y of t plus Vz dou by dou z of t is equals to k by rho Cp dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square, and then some any reaction terms etc. if at all they are existing, those things also. Similarly, dou by dou t of Ca, let us say take a binary component and then conservation of component A if you see. So then this is the equation we can write, right? dAB is diffusivity of A in B. So, we can see these equations are more or less similar to each other. Forget about these additional gravity and then reaction terms, etc. They are more or less similar, only that in the momentum equation this minus 1 by rho dou p by dou x term is there, right. So, but otherwise more or less these equations are same. Here Vx whatever is there, that you replace by T, and then in the next case you replace by Ca. Only the difference is here the mu by rho is there here, k by rho Cp is there, and dAB is here, and all of them are having the meter square per second unit. So, they are closely similar. This is the governing equation for the momentum transfer. I have written only x component. Similarly, y and z components are also possible. This is energy equation. This is the species conservation equation, whatever the species that we have taken, let us say binary system. So, for A only I have written, for B I have not written. Similarly, we can write. So, these equations are almost closely related to each other. So, if the equations are closely related, so then their mathematical approaches and then solving these governing equations can also be similar, right. So, that is the other reason that we need to study this transport phenomena course, and then molecular mechanism of these transport phenomena are also very closely related, because whether it is momentum transfer, heat transfer or the mass transfer, whatever the changes that we see at the bulk, so basically they are occurring at the molecular level, how the transport is occurring, that is all in the overall picture that we are going to see later on in the bulk phases as well. So, molecular mechanisms are very much closely related even in all these kind of transport processes. So, that is the reason, despite of having the knowledge of fluid mechanics, heat transfer and mass transfer, transport phenomena course is going to give the additional information about these processes, transport processes, and then in the due course we can understand what additional information that we are going to get compared to the individual fluid mechanics, heat transfer and mass transfer courses. Transfer phenomena can be described at three different levels: macroscopic level, microscopic level and molecular level. In the macroscopic level, what we do, we in general develop equations called macroscopic balance equations, where we take the concerned quantities or the properties at the entry and exit, whatever the inlet outlet conditions, only we are worried. We are not worried what are the changes that are going to occur because of some change in the system. So, we do not consider the details of what is happening inside the system when you make some change to the system. Okay. So, those inside details are not considered in this macroscopic level, and then in general the length scale for them is order of centimeter or meters. Microscopic level, we take the interior details of the systems also. Let us say what is happening to the fluid mixture in a small region within the equipment, how it is being treated, how it is being heated or mixed, or how it is being reacted with the other component at one particular corner, other corner. We take all these details, like we do not worry only what is the inlet and what is outlet, but we also worry what is happening, if it is mixing, how the mixing is at this particular corner, etc. If it is heat transfer, similarly heat transfer, how is varying one particular location to the other particular location, or temperature distribution, how the temperature is varying from one location to the other location. Similarly, the reaction, how good is the reaction at particular one location, how good is the reaction at the other location, is it the uniform everywhere. Those details also we can get from the microscopic level, right. So, what we do in general, we develop equations of change for mass, momentum and energy within the small region, and then length scale is order of micron to the centimeters in general. There is another level, molecular level, where the fundamental understanding in terms of the molecular structure and interaction forces are considered, but however in general chemical engineers are not worried about these kind of molecular level, but in general if the reaction or the system which is being considered is having complex molecules and extreme range of temperature and pressure, so getting involvement of chemical engineers can provide some kind of additional information, but however in general these things, molecular level transport phenomena is not much essential from chemical engineering point of view. That is, in general, theoretical physicists or physical chemists are interested in such details. Length scales in general in the molecular level is 1 to 1000 nanometers. However, whether it is macroscopic, microscopic or molecular level transport phenomena, it is very much essential to know the conservation laws play a very key role. Conservation laws play a very key role at all these three levels. We can prove mathematically also, but however, we are not going into the details of those proofs because not related to the course much. So, primarily in this course we are going to consider at microscopic level where the continuum hypothesis is valid without any restrictions. That is what we are going to study basically, and then especially this is applied to the non-Newtonian fluids. That is what we are going to see. But however, before going into the main subject, it is also important to recapitulate some of the fundamental relations, equation, concepts related to the course, which we may already be knowing, but however, it is very much essential to recapitulate this some of few fundamentals like continuum hypothesis, transport mechanism, and then constitutive equations of transport by molecular mechanism, etc. So, we start with the continuum hypothesis. Continuum hypothesis in general talks about the physical properties such as the velocity, temperature, pressure, density, stress, electric field strength, etc. and these properties are assumed to be distributed throughout the space, and every point in space has a finite value for such properties, and from one point to the next point the properties may change value, and there may even be surfaces where the properties jump discontinuously. Let us say you have a spherical particle, right, it is in a surrounding fluid. The density of the spherical particle may be very much different compared to the density of the fluid in the surrounding. So, that is this density at the interface, this density of the solid may be very high, and then immediately the very first attached fluid layer is also is having a very density very much different from the solid density, right. So, there is a discontinuity of the property, right. So, but in such cases also continuum hypothesis is valid provided the geometrical size is much higher than the molecular size, right. So, however, in the this continuum hypothesis, the main other important assumption of this continuum hypothesis is that it does not allow properties to become infinite or to be undefined at any single isolated point. So, property must be defined each and every location. So, we cannot afford to have a undefined or infinite values in the continuum hypothesis. So, precisely mathematically how we can say, like the continuum hypothesis, whatever the region in which the physical properties, let us say temperature variations or concentration variations or the velocity distributions you wanted to know, what you can do, that region you can subdivide into the small control volume like this, right. Small control volume you can divide like this. How to divide, what is the basis, that each control volume, whatever the property that you take, that should be small enough so that the property is uniformly distributed within each individual control volume. That is, within one particular control volume spatial variations are not allowed. There should not be any spatial variations. That is possible when you have a kind of sufficiently small size of control volumes. But at the same time the control volume should not be very small enough. It should be such that local thermodynamics should also be maintained. For that, it should be sufficiently large enough that large number of molecules are accommodated within each control volume. You can accommodate large number of molecules so that these large number of molecules can go through infinite number of interactions to maintain the local thermodynamics, right. So, one should be very careful in subdividing this thing in general in a small control volumes. It should be small enough that the properties should be uniform throughout the individual control volume, and it should not be very small enough that the local thermodynamic equilibrium cannot be maintained. Okay. And then from one control to the other control volume the property may change. property may change, and that property change is in general continuous, unless where the solid there is a solid, and then nearby very first layer is a fluid, the density of different density of solid and fluid, there is a discontinuity, but geometry has to be large enough in order to have a kind of this continuum hypothesis valid for the discontinuous surfaces as well, right. So, precisely each volume element should be small enough so that the properties are uniform, that is spatial variations in properties inside the volume element are negligible, and then each volume element should be large enough to contain a statistically large number of molecules so that local thermodynamic equilibrium is maintained. However, continuum hypothesis holds well provided all dimensions of systems are large compared to the molecular size. It does not hold good something like the diffusion in pores, Knudsen diffusion etc., or nano and micro scale devices where the molecular sizes are also, these dimensions of the system are also comparable with the molecular size. So, in such small dimension devices, this continuum hypothesis in general does not holds good. So, the very important aspect of this continuum mechanics is to describe the response of material to stress. So, a qualitative statement of that response is in general known as the constitutive equation, that is a model which describes how a material will respond to stress. That is what we are going to see now in the next part. So, transport mechanism. Let us say you have a kind of glass of water, right, this is the interface of the water. Now, you are dropping a kind of color dye here. So, at the point, the first point when interacted it at that interface, the concentration of dye in the water is same as its initial concentration of the dye. But as time progresses, because of this diffusion, what happens, this entire thing, the material whatever the dye is there, that is dissolved in the water, and then it becomes uniform everywhere. So, initially it is having a certain high dye color intensity, and then later on when it becomes uniform everywhere, it is having some lower color intensity, right. So, that is if you take a temperature or chemical concentration in any material are perturbed so that they become non-uniform, the gradients tend to disappear over the time. So, same is true like velocity variations within the fluid. So, whatever the spontaneous dissipation of such gradients is in general a fundamental and far reaching observation. So, over the time they come to a kind of uniformity anyway. So, from this experiment what we understand in general, the energy or concentration of material or the momentum of fluid stream tend to move from regions of higher intensity to the regions of lower intensity levels. That is higher temperature level to the lower temperature level, or higher concentration level to the lower concentration level, or higher momentum level to the lower momentum level, they usually transfer. So, fluxes of those quantities like energy, concentration and momentum flux, they have two contributions: convective transport which accompanies any bulk motion, and then molecular or diffusive transport which originates from intermolecular forces and relative motion of the molecules. So, convection part can be described in a general manner, but the molecular part of transport processes are specific to a given material or class of materials, right. So, if we go back to the these equation that we have written here, similar, see now these equations in the left hand side, these are the convection part because of the bulk motion, right. So, you can see here they are quite similar, there is nothing different from here, only thing that the velocity, temperature and concentrations are appearing in the different positions, right. So, these terms we can define in kind of general manner here, that is what we see. But here this is the viscous term, this is the conduction term, and then this is the diffusion term, right, in these three equations. So, these are also in the similar form, but they are attached with some kind of properties of the material, mu by rho, k by rho Cp, dAb etc. So, they dependent on the system properties, material properties or group of material properties. That is the reason whatever the the viscous terms, the temperature and then concentration variations there because of the diffusion, conduction and then viscous forces, they should be studied individually because they are dependent on the material properties as well. And these mechanism, the viscous component here, then conduction, the heat conduction part here and then diffusion part here, these are due to molecular mechanism, whereas these things like convection terms are due to the bulk motion, so they are similar. So here the viscous terms and then conduction terms and then diffusion terms here, they are because of the molecular mechanism and they are dependent on the properties of the material. So these three has to be studied individually, whereas the transport due to the bulk motion are there, they can be described in a general manner. So convective part can be described in a general manner, but molecular part of transport processes are specific to a given material or class of materials. Constitutive equations relate molecular fluxes to material properties, that is mu, rho, K, Cp, dAb, etc., and the gradients of temperature, concentration and then velocity, that is del square V, del square T, del square Ca, etc. It is dependent on them only. So, the molecular fluxes are related to the material properties and gradients of temperature, concentration and velocity. So, these constitutive equations we have to study individually. So, what we do? We start with the heat conduction. According to Fourier's law, heat flux vector can be related to the temperature gradient, like Q is equals to minus K del T. Q is a flux, heat flux, right? It is having the same direction as the temperature gradient direction. K is the thermal conductivity. Here in a moving fluid, heat flux vector represents energy transport relative to the mass average velocity only. Mass average velocity only, because energy flux relative to the fixed coordinates will also have the convective contribution as well, and then convective contributions can be generalized for all of them separately. So, the heat flux vector represents energy transport relative to mass average velocity only. Now, this K here does not have any preferred direction. It does not have any preferred direction, whereas the flux is having the same direction as that of the temperature gradients. Materials whose thermal conductivity is not having any preferred directions are in general known as the isotropic materials. Under these categories, most of the solids and almost all fluids are falling in these isotropic categories. But however, there are some kind of solids where the thermal conductivity also depends on the internal structure. So, thermal conductivity will also depend on the direction. So, those materials are known as the anisotropic materials. For these anisotropic material, the flux is related to this thermal conductivity tensor. Now, this is having the orientation, and depending on the internal structure, it can have different directions also. So, now the K, thermal conductivity, is a tensor. So, the Q is nothing but the dot product of this tensor and then a vector del T, right. So, in such anisotropic materials, the directions of heat flux and temperature gradient different from each other. It not necessarily be same like in the isotropic material. In isotropic material, Q and delta T are having in the same direction, right. But here it is not necessary, because now K is also having directions. Species diffusion. According to Fick's law, the mass flux of a species A relative to its mass average velocity is proportional to its concentration gradient, that is JA is equals to minus rho dAb del WA. Rho WA we can write it like this. So, rho WA is nothing but Ca. So, minus dAb del Ca, where dAb is diffusivity of A into B, rho is density of the mixture. It is not density of individual A or individual B, it is the density of the mixture. W is the mass fraction of A in the binary mixture, and C is the concentration of species A. So, this is about the species diffusion, that is the molecular mechanism in mass transfer part. The heat conduction is the molecular mechanism in heat transfer part. So, now molecular mechanism in momentum transfer part that we are going to see. So, this is known as the stress and then momentum flux. Local rates of momentum transfer in a fluid are determined by the stress. So, here what we do, we consider a point within a fluid through which an imaginary surface like this, we consider this surface we consider within a fluid. The orientation of this surface we can describe by this normal vector, normal unit vector n. So, at this point, this is the point that we have taken on this imaginary surface. At this point, whatever the stress vector is there, that can be denoted by the Sn like this, let us say, right. The stress is defined as the force per unit area on the test surface exerted by the fluid toward which n points, toward which this unit normal is pointing out. This stress vector will have two components, normal component and tangential component. One normal component, but two tangential components are shown here. So, if this is the same test surface that previously we have taken, and then it is designated by some normal vector n. So, at this point on the test surface we have this stress vector S. Now, it is having two tangential components S1 and then S2, whereas one normal component Sn. So, normal component represents a normal stress or pressure on the surface, whereas the tangential components are shear stresses. So, this whatever the stress vector is there, that can be related to the stress tensor like this, S of n is equals to n dot sigma this tensor, sigma tensor, that is stress tensor sigma, right. So, this is having two components, that is what we understand. This S is having two components. So, then this will also have two components. So, then that we can write it as sigma ij is equals to minus p Kronecker delta ij plus tau ij. If I is equals to j, then this Kronecker delta is 1. If I is not equals to j, then Kronecker delta is equals to 0. That is, if I is not equals to j, only we have the shear stress component. If I is equals to j, then we can have the pressure contribution also. So, the stress tensor whatever is there, it is having 9 components. We can write a matrix form like this, sigma xx, sigma xy, sigma xz and so on, so like this. So, sigma xx we can sigma xx in the sense I is equals to j is equals to x. So, when I is equals to j, then Kronecker delta is 1. So, it will be minus p plus tau xx, then tau xy, tau xz and so on, so like this remaining components we can write. So, what does it indicate? Sigma xy? Sigma xy indicates the force per unit area on the plane perpendicular to y axis. Perpendicular to the y axis, that y indicates the reference frame, specify a reference frame and acting in x direction. So, this x indicates in which direction it is acting and exerted by a fluid at a greater y. So, there is a sign convention also. So, sigma ij, j specify a reference plane, I specifies the direction in which it is acting, and there could be a kind of sign convention as well, greater y or greater or smaller y, something like that. So, stress may be interpreted as a momentum flux in the case of fluids, and then the part of stress that is caused only because of the fluid motion is known as the viscous stress, and then viscous stress contribution to the stress tensor is denoted by tau. And then if you have a Newtonian fluid with constant density and then constant viscosity and density, then viscous stress is related to the local velocity gradient as tau is equals to minus mu del v plus del v transport. So, where mu is the viscosity of the fluid, del v is the velocity gradient, del v t is transpose of the velocity gradient. Let us say if you simplify it, this is having all 9 components actually, whatever we have shown, it is a generalized one. So, now for a unidirectional flow with a only x velocity existing which is varying in the y direction, then this tau yx you can write it as minus mu dou vx by dou y plus dou v y by dou x. So, this is del v and then this is del v transport, right. Now, only one component Vx unidirectional flow we have taken. right. So, Vx is existing and it is varying with only y direction. So, only this term will be there. So, unidirectional flow, so other directional there is no variation at all, there is no velocity variation. So, tau yx is equals to minus mu dou Vx by dou y. This is what we write in general for a Newtonian fluid for a constant viscosity thing. Having seen the individual molecular transport mechanism for the heat transfer, mass transfer and then momentum transfer, by analogy we see what we can get. From the heat conduction equation, we can get Q is equals to minus K dou T by dou Y is equals to minus alpha dou rho Cp T by dou Y. We can write it, where alpha is nothing but K by rho Cp, and Ja we can write it as minus dAb del Ca. For one single direction it is nothing but minus dAb dou Ca by dou Y. Similarly, momentum transfer, we have tau yx is equals to minus mu dVx by dy or minus nu d rho Vx by dou y, where nu is nothing but mu by rho. So, we can see by analogy this alpha, this dAb and this nu are known as the thermal diffusivity, binary molecular diffusivity and then kinematic viscosity, and all of them are having meter square per second. What we can see, there is an analogy between this. So, what is the benefit of this? That their ratios provide comparison of intrinsic rates of different transport processes if more than one transport is occurring simultaneously. We know that they exist simultaneously, at least two of them exist at a time, sometimes more than two will also occur, right. So, then the ratio of these whatever the thermal diffusivity, kinematic viscosity etc., that we are having, that will provide a kind of a priori information which mechanism is going to lead, which transport mechanism is going to be leading, and then so that we can accordingly simplify the problem to get the restricted solutions. Let us say rate of viscous momentum transfer relative to heat conduction, if you take, that is nu by alpha. So, mu by rho by K by rho Cp, that is mu Cp by K, that is nothing but Prandtl number. Now, if this Prandtl number is small, that we can say the conduction mechanism is going to be dominated. So, momentum transfer can be ignored and then only heat conduction problem can be considered if this Prandtl number is very, very small. So, that kind of a priori information one can get in order to simplify the problem. Similarly, if you take the rate of viscous momentum transfer relative to this species diffusivity, that is nu by dAb or mu by rho dAb, that is nothing but Schmidt number. Here also if Schmidt number is very large, order of 10 power 5 or 10 power 6, we can say that diffusion is a very small and then viscous part is going to have a kind of dominating role. Likewise, ratio of diffusivities that arise in the analysis of simultaneous heat and mass transfer is known as the Lewis number, that is alpha by dAb. It can also be written Schmidt number by the Prandtl number. So, this is the advantage of writing the analogies. So, now we take simple Newtonian fluid behavior like the standard experiment. We take a Newtonian fluid confined between two plates. One of the plate, let us say top surface here, is moving with dVx velocity because of applied force F. The surface area of the plate is A. So, then we can relate the information here, whatever the velocity gradient and then shear stress is there, that we can relate, that shear stress is equals to F by A here, that is mu minus dVx by dy is equals to mu gamma dot Yx. Newtonian fluid behavior, that we know that tau Yx for this kind of one dimensional flow, unidirectional flows, this is what we know, that tau Yx is linearly proportional to the gamma dot Yx. Tau Yx is shear stress, gamma dot Yx is shear rate, and then proportionality constant mu is the viscosity, which is constant for a Newtonian fluid. If we have a flow in all three directions, so then we can for each plane we can write this sigma ij as indicated here in the figure, and then we can expand this sigma ij as minus p Kronecker delta ij plus tau ij. So, in general, this for Newtonian fluids we can have this tau xx, tau xy, tau xz expanded forms like this. So, what specifically about Newtonian fluid behavior in general? other than the constant viscosity what we can observe. So, let us say Newtonian fluid behavior in simple shearing experiment conducted at constant temperature and pressure. What the characteristics we can expect? We can say that only stress generated is shear stress and other two normal stresses individually 0 or their differences are 0, they are identically 0 or their difference being 0. That means there will not be any normal stresses in the case of Newtonian fluids. Shear stress is linearly proportional to the shear rate passing through the origin, giving a tau yx versus gamma dot yx linear plot passing through the origin, giving a constant slope of viscosity mu. And then viscosity, that slope of tau yx versus gamma dot yx passing through the origin, whatever the slope mu is there, that is viscosity, is independent of the shear rate. It is independent of the shear rate, whether you are shearing at 5-second inverse shear rate, 50-second inverse shear rate, or 500-second inverse shear rate, or 5000-second inverse shear rate. Whatever the shear rate you are sharing, the viscosity would be independent of the shear rate, provided the temperature and pressure of experiments are maintained constant. And also viscosity is independent of the duration of shearing also. It does not depend on the time of shearing also, whether are you shearing for 5 minutes at a constant shear rate, or if you are shearing for 100 minutes, 1000 minutes, or whatever, for a day, for a month, as long as you maintain temperature and pressure constant conditions, the viscosity will not change with the duration of shearing. And stress in Newtonian fluids falls immediately to 0 after shearing is stopped. Moment you stop the shearing, the stresses immediately will fall to 0, which is not true in kind of non-Newtonian fluid, especially viscoelastic fluids. And then viscosity of the same Newtonian fluid under different type of deformation is always a simple proportion to one another. Mu is the kind of shear viscosity or viscosity because of the shearing experiment. Mu E, mu double E, here given mu planar are a kind of extensional viscosity. So, in different types of shearing, if you do the shearing by different types, the types of deformations are different. One is the shearing, another one is the extension or elongation. So, there will be different viscosity obviously, but if the fluid is Newtonian, the ratio between these viscosities would be a constant. Let us say if you do the elongation or extension in one direction, then mu E, that is one directional elongation, divided by shearing viscosity mu would always be 3. Similarly, if you do bidirectional elongation, then this ratio would be 6. If you do the planar, that is in all possible directions, when you do the extension, then the ratio is 9. So, these kind of ratio, constant ratios, that in general you cannot find for a non-Newtonian fluids. Okay. So, for Newtonian fluids, these are the characteristics that in general you can mention, though you simply say the constant viscosity tau yx versus gamma dot yx passing through the origin, that is what the curve you get, that is what you say, but in general this is all the information, they are already there that you can inherently report. So, some examples if you see mentioned here in this table: air, benzene, water, ethyl alcohol, glycol, olive oil, etc. given, and then viscosities are given millipascal second units, right. So, we can see here the viscosity is the table is arranged such a way that increasing viscosity order. Air is the one lowest one here having the viscosity in this table, whatever the given material, and then viscosity is gradually increasing. Water, it is 1 millipascal second, ethylene glycol, it is 20 millipascal second, olive oil 100 millipascal second, bitumen, molten glass are order of 10 power 11, 10 power 15 millipascal second respectively. So, what we can say, increased viscosity does not mean that there will be a kind of non-Newtonian behavior. They are honey, olive oil, castor oil, these things a very high viscosity, but they are Newtonian only, they are Newtonian only. Okay. So, it does not mean that material having some kind of high viscosity, it always behaves a kind of non-Newtonian, not necessarily. It depends, like we have a very thinner material also in general showing some kind of non-Newtonian characteristics in general. These references given are found to be useful in general in this course. So many details, so many information provided in this particular course are taken from these kind of references. However, for individual lecture, what is the source of that particular lecture will also be provided in the subsequent lectures. Thank you.